Hello friends, welcome to my course on microbial biotechnology. We are in module 9 where we are discussing food production involving microorganisms and their products. Today we will be discussing about fermentation at a large scale or industrial fermentation and the health aspects of fermented beverages including their safety aspects. So, the lecture is divided into two sections. The first section deals with the industrial fermentation processes. In the second sections, we will be dealing with health and safety aspects of fermented beverages. So, we begin with scale up and commercialization processes. So, mostly the fermentation is generally experimented or standardized at the laboratory level in a very small scale. Then it is taken to a pilot scale level, and then finally for commercial purposes it has to be scaled up in a very large scale. But it is a very challenging process, and there are several issues which are crucial in this entire industrial level scaling up. For example, what is the consumer demand and the packaging impact? So, until and unless a product is in high demand, scaling up is not taken up. Increasing demand for nutritious, high quality fermented foods mostly drive the novel processes of scaling up, and advanced packaging is useful for extending the shelf life and also ensure safe distribution of those fermented food. Meeting the growing demand of the market requires improved fermentation processes and the distribution systems to handle larger production volumes effectively. Process standardization is very important, optimizing bioreactor conditions to ensure consistent product quality across diverse applications, and the source of raw materials is very important. Scaling up is a very costly affair, so the investment costs are to be considered, and innovations are important for cutting down the cost. High initial cost for advanced technologies can be therefore a barrier. But innovations like multi-starter culture and encapsulations improve efficiency and product stability. So, here is a schematics of a bioreactor. Some of the key components include the agitation system, which will mix up the media. Then the supply of acid and base to maintain the pH is very important, as well as the supply of air is very important, particularly for aerobic fermentation. Then there are an array of sensors for temperature, pH, and including understanding the airflow, and then these are helpful in monitoring the reaction conditions from time to time. Then there is a thermal jacket for cooling, and finally a effluent discharge system can be there. So, advancements in these bioreactor technology have revolutionized scalable beverage production, particularly through automation and process control. Key fermentation techniques include surface, tray, trickle bed, continuous airlift, loop, batch, submerged, and semi-continuous methods, each with broad applicability. And then automated systems monitor the different parameters and also control them like pH, temperature, and oxygen levels, and minimize human error and thereby ensure consistent product quality. Process control is very important. Therefore, real-time monitoring and adjustments such as oxygen supply regulation, maximizing efficiency, especially in large-scale production. Then self-cleaning features of bioreactors, particularly technologies like self-cleaning, microspurgers, and foam breakers, reduce downtime and contamination risks, improving production cycles. The impact on product quality is also another important issue. Automation and control lead to uniform flavor profiles and consistent quality, essential for beverages like vinegar, for example. Then there are economic benefits from this entire process. The reduced labor cost and optimized processes through automation increases profitability while maintaining high quality standards. So, let us look into the configuration of a fermentation vessel. So, here you can see a motor. Then this is the entrance to charge the reactor. Then we have a cooling heating jacket connection. We have discussed about this cooling system in the earlier diagram. Then there is a impeller you can see over here. These batch fermenters are generally upright cylindrical systems with baffles, heating cooling jackets, purgers for air circulation, stirrers with impellers, nutrient sampling ports, and gas outlets. Modern fermenters are often computerized for real-time monitoring of parameters like pH, dissolved oxygen, redox potential, carbon dioxide, oxygen in fermentation products. Sterilization is the first step before adding the microorganisms to the sterile medium. During fermentation, substrate, nutrients, cells and products change over time. Aeration supports aerobic growth, while pH control agents and antifoaming additives are used as needed. Gaseous byproducts like carbon dioxide are continuously expelled from the reactor system. Batch fermenters such as receptacle bioreactors are widely used for aerobic processes like acid and antibiotic production. However, they are less efficient for large scale production due to capacity limitations and operational inefficiencies compared to continuous systems. Batch systems are particularly suitable for processes requiring minimal contamination risks, small scale production or operations involving diverse products. Batch fermentation have several advantages. There is a lower risk of contamination or genetic mutation due to short processing times. There is reduced capital risks compared to continuous systems, greater adaptability for different products and microorganisms, higher product yield due to precise process control. However, it also has many drawbacks like lower efficiency due to downtime for sterilization, filling and cleaning, high labor and operational costs due to repeated sterilization and subculture preparation, increased risks in industrial scale sanitation, including potential exposure to harmful microbes. So, we have other type of bioreactors, for example, continuous bioreactors which are similar to batch fermenters, but feature continuous inflow of nutrients and outflow of products, maintaining a steady state. The constant conditions leading to consistent product quality and higher efficiency. Continuous fermenters are ideal for large scale production, particularly for products like vinegar, wastewater treatment and baker's yeast, where consistent output is required. Continuous bioreactors have many advantages like automation potentially reduces labor and downtime for cleaning and refilling. Stable conditions ensure consistent product quality, lower risks to operators due to mechanization, but it has many disadvantages like limited flexibility to adjust the process parameters, high capital investment for automation and equipment, increased costs for maintaining sterile conditions and replenishing substrates, higher contamination risks due to prolonged operation. So, there is another type of bioreactor which is the semi-continuous fermenters, which combine both the batch and continuous operation processes. Initially, this is run as a batch system. Substrates are later added in a controlled manner, either at intervals, batch mode or continuously, the continuous mode. Semi-continuous systems are useful when batch or continuous methods are inefficient or impractical, especially for sensitive organisms. It has many advantages like increased yield by optimizing environmental conditions during specific growth or production phases. Stability during the culture's development reduces contamination risks. However, it has also many disadvantages like time consuming process for filling, cleaning and sterilizing. It is a complex process, control requirements, higher labor and operational costs. Let us now discuss about mixed tank submerged bioreactors. The mixed tank reactor is the most common aerobic bioreactor, widely used for industrial scale applications due to its low capital and operational cost. Small scale versions are typically made of glass, while stainless steel is used for large scale operations. The design and operation of mixed tank submerged bioreactors features a height to diameter ratio tailored to product removal needs, equipped with an agitator, baffle and air injection at the base for efficient mixing, temperature control by a warm or cold water circulating through baffles, gas exhaust at the top while products are collected at the bottom. So, here the gas is expelled and then gas is injected from the below, and then you have these biomass recovery where there is a separator which separates out the product, and then it is enriched and then put into this system. Then you have a motor here, as you can see. The modern designs include advanced impellers with 12 to 18 blades or concave edge to improve hydrodynamics. Mixed tank reactors can operate in a continuous mode with consistent substrate inflow and product outflow, supporting parallel or serial configurations for enhanced scalability. Let us discuss about now fermenters for lager and ale beers. So, lager beer fermenters, modern lager fermentation primarily uses cylindroconical tanks. These were patented by Leopold Nathan in way back in 1908 and another in 1927. These tanks with capacities ranging from 100 to several hectoliters, 1000 hectoliters, and a 70-degree conical base facilitate yeast separation and eliminate centrifugation by integrating fermentation and storage. So, in this picture you can see the process for the elimination of the immature odoriferous constituents in brewing. This is a patent filed by Nathan et al. And here this is now generally has inspired many other bioreactor designed later on. Compared to open fermenters, this reduce capital cost by around 25 to 35%, operating costs by 50 to 65%, minimize product loss, lower bitter compound introduction, and enable carbon dioxide collection. So, here you can see very tall fermenters over here. These are lager fermenters, have a 3:1 or 4:1 height to diameter ratio and operate around 1 to 1.5 bars of atmospheric pressure. And then these fermenters must manage the carbon dioxide frothing, limiting fill capacity. Early tanks used glass epoxy coatings, modern ones use stainless steel 304 and 316 for chloride resistance. Some of the features include cooling, bottom filling exhaust to limit oxygen, and valve routing for control. Outdoor tanks need insulation, indoor tanks require thermal regulation. Let us now discuss about the fermenters in which ale beer is produced. Unlike the lager beer fermenters, it use top fermenting yeast and often fermented open Yorkshire square tanks. Originally, these are made from stone and slate. Modern Yorkshire squares are a stainless steel made of 304 steel. These tanks include a slanted deck, organ, funnels, and vents to aid yeast removal. So, in this figure you can see round Yorkshire squares made to modern designs to allow easier cleaning and better temperature control. Now, let us discuss about fermenters that are used in wine making. Stainless steel tanks, inox, popular since the 1970s for their ease of cleaning and cooling compatibility. Two grades are commonly used, the grade 304 which is ideal for red wine fermentation, then grade 316 which is more resistant to erosion, suitable for both red and white wines. Inox tanks come with open or sealed tops with fermentation locks, variable limit tanks, having a floating metal top with an inflatable plastic rim, allowing use when partially filled, chemically alert and beverage safe. They are easy to clean, especially with removable tops. Many include built-in cooling through these at cost. And there are alternative materials also which have been used, like fiberglass tanks. This is a cost effective option, while wooden tanks, once phased out in the 20th century, are regaining popularity in small and medium wineries for their unique impact on wine flavor. Then the red wine fermentation uses whole grapes producing carbon dioxide and alcohol. The carbon dioxide pushes grape skins to the surface, forming the cap. To ensure proper extraction and cap management, fermenters should be slightly larger than the desired wine volume to account for cap expansion. The cap must be washed with liquid wine several times daily, often achieved through a pump over process for large volumes. In the case of white wine fermentation, white wine is made exclusively from grape juice with solid removed before fermentation. Due to its oxygen sensitivity, sealed fermenters are preferred to preserve quality, while open top fermenters are not used because they are not suitable. Now, let us discuss about the vinegar fermentation tanks. Vinegar fermentation is a two-stage process. Firstly, yeast converts sugars into ethanol anaerobically, followed by oxidation of ethanol to acetic acid aerobically by the bacteria of two genera, Acidobacter and Glucanobacter, and you can see this conversion of ethanol to acetic acid. Approximately from this equation, we can find out that 1% volume by volume ethanol will give around 1% weight by volume of acetic acid. This is used to predict the eventual acidity of vinegar and to calculate fermentation efficiency. Now, let us try to remember a term called GK, which actually comes from the German word Gesamte concentration or total concentration. In the absence of over oxidation, evaporative losses and conversion to biomass, the sum of the concentration of ethanol percentage volume by volume and the concentration of acetic acid percentage weight by volume, which is known as the total concentration, should remain constant throughout acidification. This total concentration or GK yield is the GK of the final vinegar, expresses the percentage of the GK at the start of the acidification. So, in vinegar production, microorganisms form a film at the air acidifying medium interface, accelerating acidification by increasing surface area and oxygen exchange. Factors like oxygen, alcohol and microbial activity influence process. Surface culture methods use inert materials, example sugarcane, bagasse, wood flesh or vine twigs packed into tanks. The acidifying stock is splashed onto the inert material surface and streams down in opposition to the counter current flow of air. The process is semi-continuous to maintain high acidity levels. Let us have a overview of the vinegar fermentation process, which is divided into two types broadly, the traditional fermentation method and the modern fermentation method. So, here we start with the raw material and we can choose any of these methods, the traditional and the modern. There is a difference between the two. In the traditional, we use the tank, barrel, lager or surface film formation, and natural acidification takes place over there. In the modern case, we may have two different processes, the fast process and the submerged process. In the case of submerged process, like for example, the Frings acetator, here the self-preparing aerator is deployed. In the first process, we have temperature control tanks, and to these we do the inert material addition. So, overall these fermentation, we need to monitor the GK or total concentration, which was discussed earlier. Then we need to control and monitor the oxygen supply and pH and temperature control, for which there may be the process may be automated in certain cases. Apart from these, we have many variations of alcoholic fermented beverages. For example, we have alcoholic beverages from coffee byproducts. The beverage industry is exploring coffee byproducts such as pulp, husk, silver skin, residual water and spent grounds as substrates for alcoholic beverages due to their rich chemical composition. These byproducts, often discarded as waste, are promising for ethanol and spirit production because of their high carbohydrate organic matter and aromatic compound contents. And from the climate change point of view, converting waste into wealth and thereby contributing towards a circular economy concept is also driving many innovations in such waste utilization. The fermentation potential can be understood from the point of view of Saccharomyces cerevisiae, which is commonly used for the fermentation, but yeasts like Picia and Hansenia spora can also convert sugars in coffee byproducts into ethanol. For instance, H. uverum produces significant ethanol and aromatic compounds that enhance flavors. Then we have coffee pulp and husk, which are rich in sugars and create unique flavored spirits. Fermenting spent coffee grounds yields a spirit with coffee-like aromas, while pulp fermentation produces ethanol with floral and citrus notes. Then there is also alcoholic fermentation from the cheese whey, which is a byproduct of the cheese production, contains around 90% of milk volume and retains 55% of nutrients including lactose, protein contents, minerals and lipids. Its high biological oxygen demand can lead to pollution if not reused, prompting its processing into powders, protein concentrates or fermentation into alcohol. Concentrated whey 60 to 70 gram per liter lactose is ideal for fermentation, typically using Clubromyces yeast at 28 to 30 degrees centigrade. Sweeteners and fruit pulps can also enhance flavor. For example, Clubromyces marzianus fermentation yields a 35.4% alcoholic distillate with fruity esters like K. fragilis, produces spirits with toasted aromas. However, there are many challenges. For example, whey's perishability requires rapid use or cold storage. Only 2% of the yeast can ferment lactose. Enzymatic breakdown is often necessary. Combining Clubromyces lactis for lactose hydrolysis with Torulaspora delbrueckii fermentation can produce flavorful whey based alcoholic beverages. Then there have been also alcoholic fermentation of fruit beverages. Various alcoholic beverages are now produced from fruits like orange, mango, raspberry, pineapple and papaya to manage overproduction and create unique flavors. Fruit wines with an alcohol content of 5% to 13% retain nutrients from the fruit. The fermentation can be spontaneous or use Saccharomyces cerevisiae for consistency. Some fruits may need specialized equipment for juice extraction, and adjustments like sugar addiction may be necessary. Non-Saccharomyces yeast are recognized for enhancing flavor complexity and post fermentation practices such as clarification, refining the wine before bottling. Some of the examples are mango wine, which is fermented with Saccharomyces cerevisiae for 7 to 10 days. It is rich in bioactive compounds. Then we have Jabuticaba spirit and wine made from the fruit Plinia jabuticaba in Brazil, known for its antioxidant properties. Then we have papaya wine fermented with Saccharomyces cerevisiae, is high in vitamins and antioxidants, with sequential yeast inoculation enhancing aroma and flavor. Let us now go into the section 2 of this lecture, where we will be dealing with the health and safety aspects of fermented beverages, probiotics and functional beverages. With fast-paced lifestyles and changing food habits, health conscious consumers are increasingly turning to functional foods which contain bioactive compounds to prevent diseases. These foods include probiotics, prebiotics and synbiotics, which are known to improve gut health by promoting beneficial bacteria and restoring intestinal balance. So, functional foods first developed in Japan over health benefits beyond basic nutrition. They fall into 3 categories: food with naturally occurring bioactive substances, example dietary fiber, then foods supplemented with bioactive substances like probiotics, then foods containing added functional ingredients like prebiotics. These foods are commonly found in products like yogurts, sports drinks and fermented milks. Probiotics are defined as live microorganisms that, when consumed in adequate amounts, confer health benefits and are primarily associated with gut health. Common sources include yogurt, cheese and fermented products like kimchi and sauerkraut. Major probiotic strains include Lactobacillus, Bifidobacterium and Saccharomyces boulardii. Prebiotics are non-digestible food ingredients that stimulate the growth of beneficial bacteria. Common sources include oats, soybeans, barley and inulin. Synbiotics combine prebiotics and probiotics to enhance the growth and survival of healthy gut bacteria. Examples include fermented milk and supplements containing Lactobacillus and Bifidobacterium. Strains combined with oligosaccharides like FOS or inulin. Synbiotics offer health benefits such as improved gut microbiota, balance liver function, immune response and reduce infections in surgical patients. So, here we can see some invading bacteria, but then these are common cell gut bacteria. So, they will help in improve being the gut health and will safeguard the individual from these invading bacteria. So, the human gut hosts a diverse bacterial population of over 1,000 species, playing a crucial role in immune balance, pathogen resistance and nutrient absorption. Probiotics are explored as an alternative therapy for drug resistant pathogens and contribute to digestive health, reducing gut disorders and even heart diseases. Bacteria such as Lactobacillus, Leuconostoc, Pediococcus, Bifidobacterium exhibit antagonistic effects against harmful pathogens like Clostridium, Salmonella, Shigella, Escherichia, Helicobacter, Campylobacter and Candida. Synbiotics and liver health. Synbiotics help maintain intestinal microbiota balance by promoting beneficial bacteria such as Lactobacillus and Bifidobacterium. They support liver health by enhancing hepatic functions in cirrhosis patients, boosting immunomodulatory responses, inhibiting bacterial translocation and reducing post-surgical nosocomial infections. Bacterial translocation leads to the build-up of metabolites like ethanol, lipopolysaccharides and short-chain fatty acids SCFAs in the liver, worsening inflammation and lipid accumulation. SCFAs contribute to intrahepatic triglycerol formation, which drives liver steatosis. A randomized trial showed that a synbiotic formulation containing LB plantarum or Lactobacillus plantarum, Delbrueckii species, Bulgaricus and Acidophilus rhamnosus, Bifidobacterium bifidium and inulin significantly reduce the intrahepatic triacylglycerol levels and improved inulin resistance in fatty liver disease patients over 6 months. As shown in the next slide, synbiotics combat liver fat accumulation by enhancing gut microbiota, lowering inflammatory cytokines and modulating glucose and lipid metabolism. So, here in this diagram you can see that in the magnified portion how immune cells infiltrate in inflamed adipose tissue triggers the release of pro-inflammatory cytokines, interleukin 1b, 6, 10, 12 and TNF alpha and MCP1 promoting lipolysis. Here in this figure, these increase free fatty acids then enters the liver where they are converted into fatty acyl coenzyme A triglycerides and very low density lipoproteins VL DL leading to intrahepatic triacyl glycerol accumulation, inulin resistance and insulin resistance and metabolic dysfunction. Synbiotics by modulating gut microbiota help reduce bacterial translocation, liver fat accumulation and inflammation, potentially improving metabolic health. So, here is a pictorial summary of prebiotics, probiotics and synbiotics and its uses and applications. Prebiotics helps in the immunomodulation. It can be added to the poultry, fish, cattle feed, helps in preventing cancer and weight loss and cholesterol removal. It maintains the gut health, laxation and regularization and its help in the bacteriocin protein. And in the case of probiotics, we have benefits like anti-inflammatory effects, gut improvement, similarly immunomodulatory effect. It also helps us in the anti-cancer activity, relative lactose intolerance, then respiratory and UTI prevention. And in the case of synbiotics, we have many health advantages from the live microbes, stimulation of the probiotic growth by prebiotic components. So, what are some of the probiotics used in fermented foods and beverages? Probiotics not only enhance taste, but also provide significant health benefits. However, maintaining their stability during production and storage is crucial for effectiveness. Some of the examples of probiotic application in various food products are milk based products. Probiotic dairy products like yogurt, fresh and ripened seeds are well established. Prebiotic lactulose in skimmed milk boosts probiotic counts, lactic acid production and produces fermentation time. Probiotic ice cream known since the 1960s uses Lactobacilli casei and inulin to improve nutritional and sensory qualities. Other fermented dairy products like sour milk, kefir and buttermilk are less popular compared to yogurt. So, this is a probiotics bar, and these are some of the newly packaged food innovations. So, we have cereal based products like oats and barley are used to create functional foods. Cereals enriched with dried probiotic cultures serve as direct delivery vehicles for probiotics. Aiding dietary fibers improves bread's taste and health properties such as lowering digestible starch content. Studies show that barley, beta glucan and exhaust arabinoxylon oligosaccharides enhance gut health by promoting beneficial bacteria. Then we have fruit vegetable products. Fermented vegetables like sauerkraut, kimchi and lacto pickles contain live lactobacilli with probiotic benefits. Fermented cashew and apple juices have been studied for their probiotic properties. Probiotic and prebiotic infused apple wedges using Lactobacillus rhamnosus, GG insulin and oligofructose are examples of symbiotic products. Then we have the root and tuber based products. Traditional fermented products such as sinki from radishes in India and Nepal, and kanji from purple carrots in India and Pakistan contains various lactobacillus species like Lactobacillus fermentum, Lactobacillus brevis and Lactobacillus plantarum, offering probiotic benefits. Then there are functional beverages which include non-alcoholic drinks fortified with vitamins and nutrients. Examples include cholesterol lowering drinks with omega 3 and soy, and bone health drinks with calcium and inulin. In Estonia, fortified juices like Largo contain inulin, L-carnitine and vitamins to offer health benefits. In this table, we have traditional or novel food fermentations with probiotic organisms as listed. We have the species listed on the first column and the fermented foods that reproducibly contain high cell counts of the strain of the species. For example, we have Lactobacillus acidophilus, Lactobacillus casei in NS lab, long ripened seeds, Lactobacillus johnsoni in kefir, Lactobacillus fermentum in bushera, ting and other African cereal porridges and beverages, Lactobacillus plantarum in salami, sauerkraut, kimchi, olives and others. Then we have Lactobacillus paracasei in salami, vas, then NS lab in long ripened seeds. Then we have Lactobacillus rhamnosus in vili, fermented oatmeal. Let us have a very small discussion on food ethics, safety and regulations of functional food. Functional foods we now know contains live organisms. Therefore, it must meet standards before being marketed. Regulatory bodies enforce many criteria. Functional food is an ethics. Food is essential for survival, spirituality and social relationships. Ethical challenges arise with functional foods and nutraceuticals, particularly around global hunger, food safety and environmental impacts like soil erosion and pollution. Key concerns include whether consumers are aware of these products and can afford them. Safety, efficacy and awareness is also very important. Probiotics have shown efficacy reducing respiratory infections and diarrhea in children. Products like Yakult have maintained safely, but effects vary by individual, raising product specific safety issues. While efficacy is measured in control conditions, effectiveness applies to broader populations. Lower consumer awareness hinders public health benefits. Then there are legislative problems and regulations in the USA. Functional foods are regulated by the FDA alongside conventional food with no distinct definition. A 2006 GAO report called for better oversight to ensure functional foods meet claims. Key issues include safety, efficacy and the health impact. The marketing approach is also very crucial. Consumer health awareness drives the global functional food market. USA, Japan and Europe leads sales volumes, while India's probiotic market is growing at 22.6 percentage per annum annually, primarily through the sale of supplements. And then there are some major global brands which include Yakult, Japan, Actimel, Danone, France and Vifit, Campina, Netherlands. Overall, Japan leads in the nutraceutical market in Asia, while India's market is growing as health consciousness among consumers seeking fortified foods are increasing. Some of the probiotic products currently available in the market, you can see the brand name. These are examples, some of the most successful products. Acifors, which is a freeze-dried product, and it has several strains like Lactococcus lactis, Lactobacillus acidophilus, Enterococcus faecium, Bifidobacterium bifidum, and it is manufactured by Biohorma in Netherlands. Then you have Actimel, which is a probiotic yogurt drink having Lactobacillus casei and produced by Danone in France. Then we have Bacti Subtil, which is a freeze-dried product having Bacillus species strain IP5832, produced by Syntelabo in Belgium. Then Jovita Probiotisch, it is a probiotic yogurt having the strain of Lactobacillus, produced by H&J Bruggen in Germany. Then we have Provi, which is a fruit drink which has Lactobacillus plantarum and produced by Scanmageria in Sweden. Then we have Yakult, which is a milk drink containing Lactobacillus casei serota, produced by the company Yakult in Japan. Then we have Revital Active, which is yogurt and yogurt drink. It contains many probiotics, produced by Olma in the Czech Republic. Health benefits of moderate red wine consumption has also been reported. Moderate red wine consumption is linked to a 20 to 30% decrease in all cause mortality, especially from cardiovascular diseases. It increases plasma antioxidant capacity, reduces oxidative stress, lowers DNA damage, and decreases inflammation, key factors in heart disease, diabetes and neurodegeneration, obesity and cancer. So, red wine is thought to be beneficial against many of these disease conditions. And also it has been shown to be associated with lower systolic blood pressure, contributing to exercise related health benefits. So, with this we come to end of today's lecture. Thank you for your kind attention.